So, imagine you're looking at an AI analysis of a lung CT scan, right?
Okay.
The system processes the image, it prints out this very confident report, and tells you the lungs are perfectly clear.
Right, a clean bill of health.
Exactly. It tells you that you have absolutely nothing to worry about.
Mm.
But the image it's actually looking at is just riddled with cancer.
Oh, wow. Yeah, that is a terrifying scenario.
Right. The AI simply hallucinated. I mean, it saw a medical prompt, it generated a standard response for a healthy patient, and completely ignored the actual pixels indicating a tumor.
And that highlights a fundamental flaw, really, in the current generation of vision language models, or VLMs, that we use in healthcare.
They seem so advanced, though.
They do, yeah.
Yeah.
They project this aura of absolute clinical precision.
Yeah.
But underneath, they're often relying on statistical guesswork rather than genuinely looking at the evidence.
Which is exactly what we're getting into today. Welcome to the deep dive, everyone.
Glad to be here.
Today, we are looking at how researchers are finally fixing that blind spot. So whether you are prepping for a healthcare tech meeting or, you're simply insanely curious about the future of medical diagnostics, we are examining a massive leap forward in how AI processes images.
It really is a paradigm shift.
Yeah, and we're pulling from a groundbreaking research paper. It's titled MedVR, Annotation-Free Medical Visual Reasoning via Agentic Reinforcement Learning.
That is quite the mouthful.
It is, yeah. But it's a major joint effort by researchers at Tsinghua University, Damo Academy from the Alibaba Group, and Zhejiang University.
And the goal they set out to achieve here is just fundamental. It's about teaching an AI to truly look at a scan the way a human clinician does.
Right, like an actual doctor.
Exactly. To actively interact with the image, to zoom in, explore, and verify the physical evidence.
Okay, let's unpack this, because in that opening example with the lung CT, MedVR was actually put to the test against a standard AI.
Right, a side-by-side comparison.
Yeah, and when they ran the exact same cancer-riddled image through the MedVR system, it didn't just output a single text response.
What did it do?
It dynamically zoomed into the left lung, processed the high-resolution crop, and correctly spotted the cancerous nodules.
Wow.
Yeah, it actively found the pathology that the standard model completely fabricated away.
What's fascinating here is the underlying mechanism that caused that first model to fail so spectacularly.
Right, like why did it hallucinate in the first place?
Exactly. To grasp why MedVR is such a vital breakthrough, we really have to look at how current medical VLMs actually operate.
Okay.
Right now, these systems are heavily biased toward text-only reasoning.
Meaning they favor words over pictures?
Pretty much. When you give them an image and a prompt, they generate an answer based on statistical language patterns, like a textual chain of thought.
So they are essentially functioning like a hyper-advanced autocomplete.
That is a great way to put it, yeah.
Like the prompt mentions a lung CT scan, and the AI just falls into a language shortcut. It predicts the next plausible medical words based on its training data.
Right, rather than genuinely grounding its diagnosis in the fine-grained visual details of the image in front of it.
It's just guessing what a doctor might say.
Exactly. That textual prior just overrides the visual reality. But if you consider the clinical reality, human doctors do not just stare passively at a static image from a distance and make a snap judgment.
No, they're actively working with it.
Right. Clinicians interact, they adjust the contrast, they tweak the windowing to see different tissue densities.
They zoom in closely, I assume.
They do. They zoom in to look at the margins of a lesion or, the specific structure of a joint. But standard AI is entirely passive.
Just taking it all in at once?
Yeah, it takes the global image, shrinks it down to fit its processing window, and it loses all that granular interactive detail.
It's like a detective trying to solve a complex murder by only reading a brief written summary of the crime scene.
Yes, exactly.
But they absolutely refuse to walk into the room, pick up a magnifying glass, and actually look at the physical evidence on the floor.
That is a perfect analogy.
Like, you might guess the right suspect based on the summary's vibe, but you aren't actually solving the crime using the physical evidence.
Right. The AI is operating entirely on the summary level. It just lacks the mechanism to pick up the magnifying glass.
Wait, hold on, though.
Yeah.
General AI already knows how to process images. I mean, we have bounding boxes everywhere in the tech sector.
Oh, sure.
Like, self-driving cars draw boxes around pedestrians and stop signs 1,000 times a second. Are you telling me that simply handing a medical AI a digital magnifying glass, like a tool to zoom in on an X-ray, is somehow impossible without rewriting the rulebook?
Well, this raises a really important question. The barrier is not the technology of the zoom tool itself.
Okay, then what is it?
It's the annotation bottleneck.
The annotation bottleneck.
Right. In traditional computer vision, teaching an AI to use an interactive tool requires an immense amount of what we call intermediate supervision.
Meaning you have to hold its hand.
Exactly. You have to explicitly show the AI how to use the tool step by step across millions of examples.
So we would need to map out the exact thought process of zooming in for it.
Yes. You would need to hire board-certified radiologists, pathologists, dermatologists.
Which is not cheap.
Not at all. You would have them sit at monitors and manually draw millions of tiny bounding boxes on millions of scans.
Oh, wow.
Yeah, for every single image, a doctor would have to record, at step 1, zoom into coordinate X. At step 2, shift focus to coordinate Y.
The cost of doing that at scale would just be astronomical. You can't just crowdsource pathology labeling to casual internet users to save a few bucks.
You really can't. The expertise is incredibly scarce and prohibitively expensive.
So that's the bottleneck.
Yeah, and this annotation bottleneck has essentially trapped medical AI in that passive summary reading state we talked about.
Which brings us back to MedVR.
Exactly. The researchers behind MedVR realized they could never afford to build that massive intermediate data set.
So what did they do?
Well, their core innovation is annotation-free learning. They engineered a framework where the AI teaches itself how to use the magnifying glass without a single human drawing a single training box.
So it has to build its own curriculum, basically.
Precisely.
So let's get into the actual mechanics of how it pulls this off, because MedVR equips the AI with an executable zoom-in tool, right?
It does.
Like, the AI can write a short command that crops a specific region of the medical image, enlarges it, and feeds those new high-resolution pixels back into its own processing context so it can reconsider its diagnosis.
That's the basic loop, yes.
But since we aren't giving it an answer key of where to zoom, it has to navigate based on its own internal states using a mechanism called EVR, or entropy-guided visual regrounding.
Right, EVR. And the concept of entropy is the engine driving this entire exploration phase.
Let's break that down for the listener.
Okay, so in machine learning, entropy is basically a strict mathematical measurement of uncertainty.
Uncertainty, okay.
Yeah. As the AI generates a response, it is continuously calculating the probability of the very next token or word it should output.
Let me make sure I'm visualizing the math correctly for you listening. If the AI looks at a skin rash and its internal probability is split evenly,
Okay.
say it calculates a 33% chance the next word should be Lyme, 33% for mumps, and 33% for monkeypox.
Right, a totally flat distribution.
That broad flat distribution means its entropy is extremely high. It is mathematically confused.
That is the perfect way to look at it. And conversely, if it is 99% sure the word is monkeypox, the entropy is near zero.
Because it's confident.
Exactly. The AI is continuously monitoring this entropy signal, token by token.
Here's where it gets really interesting. So the AI uses this internal confusion to its advantage.
Yes, it does.
Does it just start randomly zooming into corners of the image, hoping to bump into a clue?
No, it is much more targeted than that. If the AI is generating a diagnosis and its entropy suddenly spikes, the system mathematically recognizes that it lacks the visual evidence to continue accurately.
So it knows it doesn't know.
Right. And instead of guessing and committing to a hallucination, this spike in doubt triggers an adaptive branching event.
An adaptive branching event. What does that look like?
The AI actually pauses its text generation. It takes its current state and forks it into multiple parallel reasoning paths.
So it's weaponizing its own hesitation.
Exactly. It expends a portion of its computational budget to test multiple visual hypotheses simultaneously.
That's wild.
It is. From that point of high uncertainty, path A might generate coordinates to zoom into the upper left quadrant. Path B might zoom into the center. Path C checks the lower right.
Just exploring its options.
Yeah, it's exploring the image specifically because it knows it is lost.
It is turning a fundamental flaw, model uncertainty, into an active search feature.
Which is brilliant.
And because it only triggers this branching when the entropy hits a specific threshold, it isn't wasting massive amounts of computing power zooming into every inch of a perfectly obvious scan.
Right, it's efficient.
It only deploys the magnifying glass when it needs to reground itself in the visual data.
That efficiency is key to making the model viable. But as you can imagine, this adaptive branching introduces a severe complication regarding how the AI actually learns from this exploration.
Oh, because we just created a massive validation problem.
Exactly.
Like if EVR forks the AI's reasoning into 5 different zoomed-in paths, and we don't have human doctors grading the output, how does the AI know which of those 5 paths actually looked at the causally relevant pixels?
Right, how does it know what was useful?
Yeah, how does it separate a useless zoom from a brilliant one?
And that brings us to the second mechanism in the framework, consensus-based credit assignment, or CCA.
CCA.
We need a way to assign a reward to the correct visual actions without human labels. So to do this, CCA waits until all the branched reasoning paths have concluded and generated their final diagnoses.
Then it filters them.
Yes. The first step is simple elimination. CCA compares the final diagnosis of every exploratory path against the known ground truth answer for that specific benchmark question.
So if a path got the final answer wrong,
any path that arrived at the wrong medical conclusion is immediately discarded. The system assumes that whatever region that path zoomed in on, it either contained misleading information or just lacked the necessary evidence.
makes sense. But just because a path got the final answer right doesn't mean it zoomed in on the right thing.
Very true.
It could have just gotten lucky or maybe relied on those flawed text patterns we talked about earlier.
Which is why the next step of CCA is so critical. CCA takes all the paths that successfully reach the correct diagnosis, and it analyzes their visual footprint.
And visual footprints.
Yeah, it looks at the specific coordinate boxes each successful path chose to zoom in on. And then it calculates the mathematical overlap of those boxes.
Looking for a pattern.
Right. It is looking to see if multiple independent successful reasoning paths converged on the exact same region of the image.
Okay, I think I get it. It's like a group of students taking an open book test.
Sure.
If the 5 students who got an A on the test all highlighted the exact same paragraph in the textbook, the teacher assumes that paragraph holds the correct answer.
That's a great way to think about it.
And so they reward future students for looking there.
The consensus of success reveals the causal evidence. When CCA finds this overlap, it generates what they call a consensus mask.
A consensus mask.
You can think of this mask as a localized heat map covering the heavily inspected region. This consensus mask effectively becomes a self-generated pseudo-label.
Oh, wow.
Yeah, the AI has drawn its own bounding box around the pathology without a human expert ever intervening.
And once it creates that pseudo-label, it has to alter its future behavior, right?
Exactly. It issues what the researchers call a tool reward through reinforcement learning.
Okay.
If a reasoning path gets the final answer right, and the coordinates it chose to zoom in on closely align with the consensus mask, the AI receives a high reward signal.
Reinforcing the good behavior.
Right. It mathematically reinforces the neural pathways that led to that specific tool use. So if we connect this to the bigger picture, you can see how the two mechanisms create a closed learning loop. EVR acts as the relentless explorer, venturing out into different visual regions whenever it senses its own doubt.
Right.
And CCA acts as the strict supervisor, finding the hidden ground truth in the consensus of those explorations and doling out the rewards.
They form a completely self-taught curriculum. I mean, the AI uses its doubt to explore and its consensus to learn.
It really is an elegant system.
The theory is incredibly elegant, yeah, but theories in AI research often fall apart when they hit the messy reality of clinical data.
They do.
So let's look at the actual proof of concept. Did the researchers prove that EVR and CCA actually result in a better diagnostic tool?
The empirical results are incredibly robust, actually. The team evaluated MedVR across 6 major publicly available medical visual question answering benchmarks.
Really putting it through its paces.
Yeah, these data sets are designed to push VLMs to their absolute limits. They used 𝗲𝗎-VQA for complex multiple choice diagnostic reasoning and data sets like SLEC and PathVQA for open-ended free text generation.
So across various modalities, radiology, pathology, dermatology.
Exactly.
And these aren't just simple, is there a bone broken, yes or no tests.
No, not at all.
These require deep, multi-step clinical reasoning.
And MedVR set new state-of-the-art records across these benchmarks. It didn't just marginally improve on baseline models either.
It beat the big ones.
It outperformed general-purpose heavyweight models like Qwen 2.5. And more importantly, it beat specialized medical-specific models like Linshu 7B.
Wow.
Even models that had significantly larger parameter counts.
It proves that teaching an AI how to actively reason and verify its evidence is exponentially more powerful than just dumping more parameters and raw data into a passive model.
100%.
But diving into the paper's ablation studies, there's a finding that really anchors why this specific framework is so necessary.
Well, the ablation studies are crucial. They involve systematically disabling individual components of a complex system, to isolate what is actually driving the performance gains.
Right. And the researchers ran a test where they gave the AI the executable zoom-in tool, but they completely disabled the EVR exploration trigger and the CCA consensus rewards.
Oh, no guidance.
Right. They effectively handed the AI the magnifying glass and told it to figure it out on its own without the self-taught curriculum.
And what happened?
The AI's performance actually degraded. It performed worse than a baseline model that had no zooming capabilities at all.
Which is a counterintuitive finding, until you think about the cognitive load of tool use.
How so?
An AI does not inherently possess zero-shot reasoning capabilities for novel tools.
It doesn't just naturally know how to use a magnifying glass.
Exactly. If you introduce a mechanism to drastically alter its visual input, like cropping and zooming into random pixel patches, without a sophisticated structured reward signal to guide why it should zoom, the tool simply acts as a distraction.
It just confuses the AI.
Yeah, it introduces unproductive search paths. The AI zooms into a patch of irrelevant healthy tissue, fills its processing context with useless high-resolution pixels, and completely derails its standard reasoning process.
I see.
The ablation study proves the AI desperately needs the self-supervision of EVR and CCA to learn how to wield the tool effectively.
Giving a tool to a system that doesn't understand its purpose just creates more noise. The framework is what matters.
Absolutely.
To make this concrete for you listening, let's walk through 2 of the real-world clinical case studies highlighted in the research. These examples vividly demonstrate the leap from passive guessing to active visual reasoning.
These are great examples.
The first involves a complex dermatology presentation. A patient has a distinct skin lesion.
Right. And when a standard passive VLM is presented with this case, it takes a global view of the image. The lesion is visible, but it's small.
And the prompt asks for a diagnosis.
Yes. But because the model relies on textual priors associated with general rashes, and it cannot verify the fine details, it just outputs a guess.
Like Lyme disease.
Lyme disease, or perhaps mumps. It is leaning on statistical likelihood rather than the specific physical reality of the patient.
But MedVR processes the exact same initial image, and its internal architecture reacts completely differently.
How so?
It takes the global view, begins to formulate a response, and immediately registers a spike in entropy.
It senses that doubt.
Yeah, its probability distribution for the diagnosis token is flat. It recognizes its own uncertainty, and that triggers the EVR branching.
Right.
The AI halts its text generation and executes the zoom tool, cropping tightly onto the specific coordinates of the skin lesion.
It pulls those high-resolution pixels into its context window. So now, instead of a blurry, generalized rash, the AI's visual encoder can process the minute structural details.
And the system's reasoning updates dynamically.
It does. It notes that the zoomed-in structure is specifically a nodule with a central depression.
That is a highly specific morphological feature.
It is.
And because the AI grounded its reasoning in that verifiable zoomed-in visual evidence, it completely discards the Lyme disease hallucination and accurately diagnoses monkeypox.
It actively found the clue it needed.
It really did. And we see the exact same transition from passive guessing to active verification in radiology, too.
Yes, the MRI study.
Consider the paper's case study involving an MRI scan of a shoulder. The prompt is open-ended, asking the system to observe and diagnose any pathology present in the joint.
And for a standard model, an MRI slice of a complex joint is incredibly noisy.
So much going on.
Right. Faced with that visual ambiguity, the passive AI resorts to generating the most common textual associations for shoulder pain.
So it outputs a diagnosis of a torn ligament or a general bone fracture.
Exactly. It is a statistically safe guess, but clinically useless.
But MedVR detects the high entropy associated with the complex joint structures. It triggers a branch and dynamically zooms its focus specifically into the labrum area of the shoulder joint.
It knows where to look.
By isolating that region and processing it at a higher resolution, the AI's visual encoder identifies a highly specific anomaly. It spots a distinct high signal intensity circle within the tissue.
It zeroes in on the subtle pixel variation that the global view obscured.
Yeah. And because it verified that specific high signal circle, the model overrides the generic text probabilities. It correctly identifies a labral pathology.
Which is impressive.
Very. This is a highly specialized, nuanced diagnosis that demands precise visual confirmation. The AI acted like a clinician, moving from a general survey to a targeted investigation.
It's a huge step forward.
So what does this all mean? When we step back from the technical mechanics of entropy spikes and consensus masks, what is the core impact of the MedVR framework?
Well, it proves that we have found a mathematical, scalable way for artificial intelligence to overcome its own text-based hallucinations.
Which is massive.
By giving the AI a mechanism to actively explore when it is uncertain and a way to verify visual evidence through consensus, we are bypassing the massive, prohibitive cost of human data labeling.
The critical takeaway for anyone working with or relying on health technology is that this bridges a massive trust gap.
Trust is everything in healthcare.
It really is. The industry is currently struggling with unreliable, hallucination-prone AI prototypes that look great in press releases, but fall apart in actual clinical workflows.
MedVR moves us significantly closer to deployable, trustworthy medical tools.
A clinician can actually trace the AI's reasoning. They can see exactly where the AI zoomed in, look at the consensus mask, and verify the physical evidence the AI used to make its diagnosis.
The reasoning is transparent and grounded in the actual pixels of the patient's scan.
It elevates the AI from a system that generates statistical summaries into a system that actively participates in the diagnostic process.
Active participation is the key.
It really is. But I want to leave you with a final thought to mull over, something that takes this concept of annotation-free learning and pushes it into a completely different, almost science fiction realm.
Okay, I'm intrigued.
In this paper, we saw a diagnostic AI use its own mathematical uncertainty, its own measurable doubt, to teach itself how to visually navigate complex, unlabeled, two-dimensional medical images.
Right, the entropy signal acting as the catalyst for self-taught exploration.
Exactly. So what happens when we take this concept of self-taught exploration triggered by doubt and apply it beyond software to AI navigating the physical, three-dimensional world?
Oh, wow. Like robotics.
Consider the robotics industry or autonomous vehicles. Right now, those systems rely heavily on massive data sets of human-labeled environments. Could we see a future where physical robots use their own internal entropy to master totally alien, unlabeled physical environments?
That is a fascinating extrapolation. If a rover on a distant planet encounters a geological formation it doesn't recognize its entropy spikes.
And instead of freezing or crashing or waiting for a delayed signal from a human controller, it uses that doubt to seamlessly branch its physical sensors.
Testing possibilities.
It repositions its cameras, tests multiple physical hypotheses in real time, finds a consensus among its sensor data, and builds its own understanding of reality on the fly.
Self-supervised learning in the real world.
Yeah. We gave a medical AI a digital magnifying glass, and it used its own hesitation to teach itself how to use it. It makes you wonder what happens when we give an AI a physical body, and it uses its doubt to teach itself how to look around our world.
Moving from passive observation to active, self-supervised perception is really the frontier of autonomous systems.
It changes the entire paradigm of how machines interact with their environment. We'll leave it there for today. Keep exploring, keep questioning the evidence, and never forget to pick up the magnifying glass.